So new unit is on momentum, and our momentum equations are here on the formula sheet. So we were here, we kind of skipped this section and went over in this one. There's 4 equations. Of the 4 equations, I'm going to introduce 3 out of the 4 today. Really the first 2 are just things that we're going to use for the third, and we'll use the first one for the 4th equation. But momentum, the equation is the one on the left. It's P is equal to m times v. It's a lowercase p. Why the letter P for momentum? I have no idea. I should look it up sometime. I just say that every year, like I have no clue why they picked that. It might have something to do with maybe some Latin derivation. Don't know. And I haven't cared enough to look it up. I guess that's really why I don't know. But pretty common they use P. Where M is not for momentum, M is still mass. We're consistent with that at least. Uppercase P was power. Remember, power is work divided by time. This is a lowercase p, and this is mass times velocity. So velocity is meters per second, mass is in kilograms, and then our units for momentum is simply taking mass, kilograms, times meters per second is kilograms times, that's dot means times, kilograms times meters per second. Or another acceptable unit for momentum is Newton's seconds, or Newton's time seconds. And right now, it's not super clear where that one comes from. It actually comes from that third equation. We'll talk about it when we get there. But both of those are acceptable units. Doesn't matter which one you use. I probably use Newton's seconds more common, or more frequently, I should say, than kilograms times meters per second, just because it's 2 letters versus 3 with a slash in it. I don't know. But it really doesn't matter. A couple things to note about momentum is this is a vector quantity. And remember, vector is applying for a new type of a new villain loan. I don't remember the exact part. Anyways, vector commits crime with both direction and magnitude. Oh yeah. So we need to make sure we have a direction associated with momentum. And where that direction comes from is it comes from velocity, because velocity is also a vector. So if our velocity is to the right, my momentum will be to the right. If my momentum is, or if my velocity is south, my momentum will be south. And oftentimes we use positive and negatives. Okay, so we have keeping our same convention. Right is positive, left is negative, up is positive, down is negative. If we talk about those in terms of velocities, then we can keep our momentums, and that will give us directions there. But we do need to include directions with our velocity, which then in turn give us the direction for our momentum. So if we were simply asking, like, how much momentum does an object have, it's pretty straightforward. We take the mass of that object times the velocity of that object, and that gives us the momentum. Momentum does have, I don't know what I was going to say there. That didn't make any sense what I was going to finish with. When we calculate momentum, you must have a velocity in order to have momentum. You currently have no momentum if you're just sitting there. If your velocity is 0, you have no momentum. It doesn't mean you can't interact with an object. Like if I were to throw a bowling ball to you, and you were to catch it, not at you, to you, notice how I use the word to you. If it was a smooth enough surface, you and your desk, when you catch it, might actually start to slide. And that would be a type of interaction that we're going to talk about, or collision. And we could talk about momentum being conserved and other things like that. But you can be part of an interaction with no starting momentum. Okay, so you have to have velocity in order for those to be momentum. So sometimes when we talk about objects, they will come to a rest, which means they end with no velocity, which means they end with no momentum. Or we could say they start at rest, which means they start with no velocity, which means they start with no momentum. Sometimes we want to compare the change in momentum, and that's what the second equation is delta p, or a change in momentum, And all that's going to be is if you take the final momentum minus the initial momentum. So it's two location problems using 1s and 2s like we did last time. Final minus initial, and it has to be final minus initial. It's not initial minus final, it's final minus initial. So if my final momentum is bigger than my starting, then I have a positive change, but if this is smaller than I started with, then it's a negative change, which indicates things. Now, this equation is on your formula sheet. This equation is on your formula sheet. And the reason why this one is on your formula sheet is for the next one. But I want to point out something, that this isn't the most user-friendly equation. It's fine. But how do you calculate P2? Well, it's m times v. How do you find P1? The idea is if we were to expand this, instead of talking about P2, well, P is m times v, so P2 is m times v2. And then we could say, well, P1 is m times v. And order of operations is important. We do the multiplication before we do the subtraction. And some of you might look at that and say, hey, I could factor out a m, and we could say m times the quantity of v minus 2, not the quantity, the difference of v2 minus v1. Yeah, you could. But that's what delta p means. It's your final momentum, which is m times v2, minus your initial, which is m times v1. And lots of different situations we could look at. We could look at collisions of a car, we could look at you jumping and landing on the floor, we could talk about an egg being dropped and hitting the floor. Lots and lots and lots of different things. Generally, we don't do a whole lot of what's the change in momentum, but where that change in momentum does come into play is in the third equation on our list. Delta P is equal to F times delta T, which is equal to impulse. So that's referred to as that equation, the momentum impulse theorem. And the idea of that is really taking a look at an object's change in momentum and how that affects it. Now, impulse is what this is equal to. And if we talk about like A is equal to B and B is equal to C, we could say, well, what's the impulse? If I say, well, what's the impulse of, we could go force times delta T. That'd be one way we could solve for impulse. Or we could say impulse is equal to your change in momentum. And how do we calculate change in momentum? We use our change in momentum. So that's really where that second equation is probably most frequently used, is to use it in the third. And when we talk about the momentum impulse theorem, we can look at this a couple different ways. Sometimes we look at this to talk about what is going to have the greatest change in momentum, or the greatest change in velocity in essence. Or we could say what's going to have the biggest force or the smallest force. So when we talk about change in momentum, again, you can calculate it that way. That number is a number we can use to figure out the force in our time. And our time is what I'm going to refer to as time of impact. Now, the reason I'm calling it time of impact, first of all, is I'm going to show you some video of car crashes. And our impact, they crash with stuff. Because most of the time when we deal with objects changing momentum, it doesn't have to be, but normally it's some form of a collision or some type of something like that. This could be like applying a force with a tennis racket on a tennis ball, which causes the tennis ball to change its momentum. This could be applying a force on a bullet throughout the barrel to cause the change in momentum of the bullet flying downrange. This could be the force times time of impact of a football player tackling someone, causing a change in momentum of that player. Now these are all dealing with an object. This is what is the momentum of a object. This is what is the change in momentum of a object. This is what is the change in momentum of that object, and the force on that object times the time of that object is an impact, time of impact of the other. So these are really just one object things. That fourth equation, which we're not going to talk about today, is what happens when two objects interact, and we're looking at both at the same time. So, when we talk about these things, change in momentum is mass times change, v2 minus m times v. So, let's just say I'm driving a car with a certain mass at a certain speed down the road. And I see, I don't know, all of a sudden a wall jumps out of nowhere and I run into a cement wall. So my car is traveling at some velocity and it hits the wall and comes to a stop. So I have the same mass of the car, I can calculate my masses, the change in momentum of my car. Okay. So my final, if I come to a stop, my final momentum, final velocity is 0. So my final momentum would be also 0. So I'm going to have a change in momentum that's 0 minus some number. Okay, now my change in momentum, 50 miles, what did I say, 50 miles per hour? Sure, 50 miles per hour. I'm driving at 50 miles per hour. I run into a cement wall, my car comes to a stop. I have some change in momentum. Okay? Kind of envision that crash. Not good, right? Generally not. Now, I'm driving down the road in my same car prior to the collision, because I haven't crashed it yet. I'm driving down the road in my car at 50 miles per hour and I run out of gas and my car coasts to a stop, so it has a final velocity of 0. How does my change in momentum compare to crashing into a brick wall versus running out of gas? Is my change in momentum for the crash and gas the same? Is my gas change in momentum bigger, or is my crash change in momentum bigger? Which one has a bigger change in momentum? Running out of gas and coming to a stop when I was going 50 miles per hour and I coast to a stop? Or I'm going 50 miles per hour and I crash into a brick wall and come to a stop? Which one's change in momentum is bigger?
Brick wall.
I heard brick wall. Anybody have any other opinion beside brick wall? They're the same. I heard they're the same. Anybody want to say the running out of gas? Okay. They are the same. Because what's true about my V1, my V2, and my mass in both of those situations? They're all the same value, right? My initial velocity was 50 miles per hour. My mass in my car was some made-up number that I didn't even make up. But my final velocity was 0. They have the same change in momentum. Are those two situations the same exact situation then? Is the end result the same? Well, no, they're very different, right? I smash into a brick wall, my car and me maybe get really messed up. Or if I coast to a stop, just coast to a stop. So what's the difference? It's not the change in momentum part of those two collisions or interactions that is different, but it's the force that's exerted over the time of that change in momentum. So is it really an impact if I coast to a stop? No, it's not really an impact. But the idea is if I coast to a stop, the amount of time it takes me to coast from 50 to 0 is going to take a while. How many seconds? I don't know. I don't care. 10. It's going to take me 10 seconds to coast to a stop. But if I hit a brick wall or cement wall, this time of impact is going to be really, really small. Made up number, 1 second. That's probably way too long just for the record, but let's just make it 1. My change in momentum is going to be the same. This change in momentum is going to be the exact same, but my time of impact is much different. So if my time of impact of the wall is 1 second, and me coasting to a stop is 10 seconds, the force is going to be much, much, much different. Factor of 10, right? So if I have a tenth the amount of time, that means my force is 10 times greater than it was coasting to a stop. Again, those are made up numbers, but the idea is there. My situation is the same. So the idea when we talk about cars and we talk about collisions of these cars is we can go through and we can make sure that we address these appropriately. So when we look at these, this is a couple car crashes that I have. My video, I'm not going to put that there just because then I'd have to edit it out or I'd get copyright flagged. So that's okay, there's like no sound. Anyways, so this is two different collisions. This is a 2006 Lexus GS300 running into a frontal crash. And, okay, so the car smashes, and they show this from a bunch of different angles. It's not a head-on, it's kind of hitting in the front quarter, and then we go slow-mo here. So whatever the car's speed was, and this is a standardized start speed, I just don't know what that standardized speed is. It's going a certain speed and it hits the wall. It does bounce back slightly, but it ultimately comes to a stop. So whether you are in this car or you're on your skateboard going the same speed, which would be impressive going that fast on a skateboard, be a very bad result. But the idea is if you start at the same velocity and you end at the same velocity, your change in momentum, no matter what it be, your skateboard would have a very different mass, but your change in momentum is going to be the same, but the result or the safety of the people in it is going to have a significant impact. Okay, so your change in momentum in the two situations in the car that I talked about is the same, but the idea is when they build these cars and they do safety testing on it, what they're trying to do is they're trying to minimize the force. They're trying to make this as small as they possibly can. Well, maybe not as small as they possibly can, but as small as they reasonably can is maybe a better way to put that. Because if the ultimate goal of designing the car is to be a functional car and safety, we want to try to minimize the force acting on an occupant in the event of an accident, right? So what are some things that they do when they build a car to try to, and if you were involved in that collision that we just saw, that would help reduce this force? What are some safety features that they do with a car, that they built into a car, to help reduce this if you were in that car during that collision?
Airbags.
You have an airbag. Now what does that airbag do? It decreases the force, but what it really is doing is it increases the amount of time that it takes you to come to a stop. You're still going to stop, but that airbag inflates, you hit that airbag, it cushions your head, it increases that stopping time, you bounce backwards, but it does increase this time. And you could say, well, is that really that big of a difference? Well, if this whole collision were to take, let's just pretend 1 second, probably too long, but let's just pretend it took 1 second. If we could add 1/10 of a second, okay, 0.1 out of 1 is a pretty big chunk. Or if we could add 0.2 or 0.3, every 1/10 of a second we add decreases this by a factor that we increase the time by. So if we were to say double the time, so from 1 to 2, which would probably be too much, but if we were to double the time, that would cut our force in half. Okay? So we use airbags to help increase that stopping time. What else do they do to help reduce the force of you when you're in a collision? Airbags is one. We often hopefully don't. Seatbelts, yeah, we don't hopefully think about seatbelts. Hopefully you all wear your seatbelt. But that also increases your stopping time. Another thing a seatbelt does, which is very significant, is it keeps you with the car. it keeps you with the car or in the car. So if you were in a collision like this and you didn't have a seatbelt, there is the possibility that you could be thrown up and out the windshield, and then you're not being protected by anything. Now, there are some people who say, hey, but I know this one situation where if they would have been wearing a seatbelt, then I've heard those too. And I'm pretty sure I know of one of those, a person who actually had one of those situations. But those are really, tends to be exceptions, not the norm. Generally speaking, you're in the car, you're going to be better off than being thrown out of the car in the process, right? So seatbelts keep you with the car, but they also increase that time. There's another thing, and maybe you know it or maybe you don't, that also increases the time during the collision. It's the front end of the car. And if you watch some of these collisions, and I got another one. There's another collision that I'll show you, but the front end of these cars are designed to crumple. They call it a crumple plate. And when the front end hits something, it's designed to like crush. But the idea is as it crushes the back of the car, you are still moving forward. You're slowing down while moving forward, but it's again increasing that amount of time that you're moving to come to that final stopping. Okay, so there's the crumple zone, there's a seatbelt, and airbags. Seatbelts, hopefully you all wear seatbelts. I'm guessing most of the cars that you ride and drive in probably have an airbag anymore. Not all of them, I know that, but a lot of cars do. It's become a fairly common thing in the cars in the last X many years. That wasn't always the case. If you go back far enough, there's cars that didn't even have seatbelts in them. Okay, there was no seatbelts in the car. Or if you had a car that did have a seatbelt, it might be a lap belt only. And that's better than nothing, but in the event of a collision, it kind of bends you in half and kind of doesn't hold your head and your body back. So you'd smash it on the dash or the steering wheel. Okay, so seatbelts, specifically a shoulder belt, and then that crumple zone in the airbag is kind of what we've done. So this next video that I'm going to show you it's a collision of two cars. So they take two cars, and instead of smashing them head on, they stagger them. So it's like quarter to quarter, front half to front half kind of thing. And they take a 1959 Chevy Bel Air, and they run it into a 2009 Chevy Malibu. So an older car and a newer car. Now when this video was actually made, it probably was a new car, but it's not 2022, but whatever. It's a newish car, so 09 versus 59, so 60 years apart. I always like to show this video. It does a really nice job of showing how cars, like safety of cars has changed in 60 some years. Wait, I did my math wrong, sorry, 50 years. That's a 50-year difference, not 60 years. And it reminds me of a story, and I like telling stories. Once upon a time, the year was 2000. You guys weren't born yet. The year was 2000, and there was a young driver driving down the road in his parents' really new car that was like 7 or 8 months old. And the roads are slushy, and it was snowing, and it was four-wheel drive, and he thought he could do whatever he wanted because he had four-wheel drive, and he was young and foolish, and just I'm going to pass some cars. He was going to pass some cars on the highway, only to get stuck in some slush and went into the farmer's field and rolled and totaled his parents' car. Everyone was safe, walked away, we were fine. And they were fine, they were fine. But the car was totaled, okay? Car crushed, airbags did not deploy, but we were all wearing our seatbelts. Luckily, the friend put their seatbelt on about 20 minutes before the accident happened. The driver was me, by the way, if you didn't figure that one out. And again, we were fine. I was pretty shaken up by the whole thing. I didn't want to drive for a while. It was kind of a scary thing. If you've ever been in an accident, it's nerve-wracking. And you question yourself and whatever. So my grandpa told me a story to help me. He's like, you know, when I was a kid, in the good old days stories, right? So back when I was a kid, I rolled my dad's car too. I'm like, oh yeah? He's like, yeah, me and some friends, we were out and we were driving around and I drove it into the ditch and I rolled my dad's car. I'm like, oh, okay. And was everyone fine? Oh yeah, we were fine. We were fine. He said, I never even told my dad that I did it. I'm like, wait, what? You never told? Yeah, I probably nah, I didn't tell my dad. I'm like, how did you not tell your dad? He's like, well, he was kind of mad because I broke this side mirror off the passenger door. But other than that, like me and my friends, we just pushed it back on its four wheels and we drove home. And I'm like, what? He's like, yeah, we just pushed it back on its, all got on one side, we pushed it back over and we drove home, but we broke the mirror off. So I'm like, well, what? How does that work? Like I totaled my parents' car that was only a couple months old. You didn't even tell your dad. You should tell your parents if you get in an accident, even if it's, they don't know. Like, oh, I broke a mirror. Like I rolled a car. Moral of the story. Anyways. But, you know, it's one of those, like, back in the good old days, they made a car like that was a car, and they were durable, and nowadays you sneeze on them and they dent. That kind of thing, right? That's kind of the story that I can kind of envision my grandpa, if he were to elaborate it on it, would hold. So they take a 1959 big old boat of a car, we would often call them boats, and they run it into an '09. The thing that I want to point out is the safety issues, or the changes that have occurred over those times. So again, 59 Bel Air, pretty big car, and they run it into an '09 Malibu that looks like that. So both of these cars are probably a total wreck, obviously, when we're done with this. But the important thing is vehicles are material things, or people in it are the important things, right? So we smashed two cars into each other and watched the car, the passengers, the doors, the location where the passengers are. Because those are the things that we really matter. We're never probably going to drive either of these cars again, but is the people in the car going to be able to drive a car again? That's kind of the thing to think about. So a couple views that I really like is the next one. It's kind of like sitting in the back seat. They show the camera. And things to watch is watch the steering wheel, watch the roof of the car, watch the passenger, and the seat itself. This view right here. This is probably the best view. Okay? So that's probably one of the best views to watch. Then they're going to switch to the Chevy Malibu. And then when we watch that same view again, the roof, the seat, the steering wheel, the head. So here's the angle from this one. Same angle. Okay, so things that have changed in the 50 years between these two cars is if we look, they're going to take the door off in a second to show you where the passenger is. If we look at, I don't know why I didn't go full screen on this, I apologize, I should have done that. If we look at like the passenger and where the passenger is, that area that they were has been compromised, right? It's bent, the front bumper is actually right here in the whole thing. But like his knee, the steering wheel, you hopefully saw the roof. If not, here, I'll show you again. Watch the roof hit his head, watch the dash, watch the seat, you know, the whole steering wheel moves. And then again, watch that same area for the Malibu. Airbag deploys, shoulder belt on, but the idea is that area that the passenger is relatively unchanged. Besides some flying debris, the seat jerking, the head's airbag, stuff like that. But like if you look at the roof, you look at the dash, the steering wheel, besides some vibration, it's still like where it should be, right? It's still pre-crash location. So when they go through and they design these cars, again, airbag increases that stopping time. The seatbelt increases the stopping time, as well as keeping you in the car. And they build the front ends to not do that. Okay? They try to make the car crumple, but not break, to maintain the structural integrity of where the passengers are. And this front end is designed to go like this while this stays solid. Because in those two situations, this one has, let's just pretend the mass of the cars were the same. They were going the same starting speeds, they were going the same stopping speeds. Their changing of momentum, their change in momentum of the 59 versus the 09, let's just pretend were the same. The 59 is probably a heavier car, probably had a little bit of momentum, but let's just pretend it wasn't. But now if we talk about what is the force exerted on the passenger, that's breaking bones, that's injuring them. The Malibu is going to have much smaller forces because the time that it took that person to come to a complete stop was significantly larger, bigger than in the 59. If this is the same, but this is bigger, this is going to be smaller. If we were to say double the time of impact, we could cut the force in half. Now, whether we can really double it, I don't know, but that's that idea. Okay, now there's other situations that we could talk about that deal with kind of the same thing. There's, I don't know if I want to do that. No. You know, there's, like, if you were to jump off of, like, the table, and you were to, like, jump onto the floor, you probably, I would suggest, you not land legs straight and jump down, because it'll not do good for your knees, right? You bend your knees. And
Dear mirror, how do I see myself? I see power. I see generous.
When you land, you bend your knees, you absorb that shock. You increase that time of impact. And by increasing that time of impact, you're going to, excuse me, by increasing that amount of time of impact, you're going to decrease that force on your joints. A long time ago in college, I took a class. It was a military science class. And we went to Fort McCoy for a weekend in it. And there was like an airborne tower. And one of the things we did is we like stepped out of a pretend, well, it wasn't pretend, an old fuselage of an airplane. And we had like a parachute harness on. And we practiced like landing. And the idea of when we were to like land if we had an actual parachute on, which we didn't, but we had all the harnesses on, is we were supposed to be knees bent, and then when we land, we bend our knees, increase the time of impact, and then we were to fall to the ground. I'm not going to fall because I probably hurt myself in the falling process here. But then you were to fall, and by falling, then you were supposed to fall to your side, and you were supposed to like absorb it and like up your side. All of that was to increase that time of impact to try not to break your legs when you landed on the ground. We were jumping out of a plane fuselage that was this tall for the record when we did it, but it was a practice. It's like what they would do. But that's the same thing that they, like if you were to actually like go skydiving. Now the really good skydivers you watch, like the ones that land in like the football stadiums with the flags, they pull on those things, I don't even know what they're called, and they're coming down and it kind of pulls them up so then they can kind of just walk. Well, their time of impact is really, really big, and their force is really, really small because they change that momentum right at the very end. If we take a look at the first problem on here, and that might be about all the further we're going to get today, this is really just taking a look at momentum, a change in momentum. So this is saying if we had a ball that's 0.2 kilograms that's being thrown at a wall at 3 meters per second. If it hits the wall and it bounces straight back with the same speed, so it was going at 3, it's still going at 3. What is the ball's change in momentum? So this is one object that we're looking at, but at 2 different locations. The question is asking what is the change in momentum of that ball? And the way we calculate that is we change in momentum is P2 minus P1. And the way we can calculate, and this is fine, I like this version a little bit nicer, is we can say delta P is equal to M times V2 minus M times V1. Now there's some important things to keep track of here. and it's m, right? There's my m. My mass is going to be the same before and after, so it's going to be 0.2. But it's the direction of the speed. So it moves in at 3, it comes out at 3. The speed is the same, but this isn't mass times speed, this is mass times velocity, and velocity has a direction. So my v1, according to my picture, is moving to the right, is going to have a positive 3. My v2 bounces straight back, but in the opposite direction. Straight back means the opposite direction. It's going to be moving at negative 3. So my change in momentum is equal to mass times v2, and my mass is 0.2. My v2, this is v2 right here, we got to go final minus initial, is going to be minus 3. That's my p2, m times v2. And that's going to be minus my m times my v1, which I'm going to put a plus 3. Don't really need to put the plus 3, but I'm putting it there to kind of make the point. And a lot of people look at this and say 0. It's 0. Positive 3, negative 3, that's a change in 0, but it's not. Because when we do the math here, my change in momentum is equal to negative 0.6. Positive times a negative is a negative. Minus a positive times a positive is a positive, and my positive is 0.6. So negative 0.6 minus 0.6 is not 0, it's negative 1.2. And you have a choice of whether you use Newton seconds, which is the one I said I frequently use, or it's kilograms times meters per second. One of the two. Change in momentum is final minus initial. You got to keep track of directions of your velocity, because the directions in your velocity affect the direction of your momentums, which then affect the change in momentums. Tomorrow, I don't think I have time. Tomorrow we're going to do, and you may have done this in another class at some point throughout your school career, but I don't care. You're going to design a device to drop an egg, right? You probably have done this at some point, and I don't care. So the idea that if an egg is going to be dropped from some standardized height, and it hits the floor, if I were to just take an egg and drop it, it's going to break, it's going to crack, because the force is big enough to crack the eggshell and go splat. If we want to save the egg, then we need to decrease the force. So in decreasing the force, you have a couple options. Most people increase the time of impact, right? The airbag, if you increase the time, you put an airbag in your car, your force decreases. If you increase the time of impact of your egg when it hits the floor, you're going to decrease that force. Or if you change the change of momentum, so really the egg's going to go to a stop. You're not stopping. The egg is going to stop. So your final momentum is going to be 0. Depending upon how fast that egg is coming in when it first touches the ground, though, that's something you might have some impact on. And you can maybe change. And if you increase the velocity or you decrease that velocity, that's going to change that momentum. By changing that momentum, you could then decrease the force that way. Okay, so that's tomorrow. That's something we're going to do. So kind of be brainstorming some ideas. I'll have some quasi-limited supplies for you to use, but that's tomorrow's activity.